In the next section, our third keynote speaker will be delivering her keynote address entitled Material Designs for Distributed Carbon Capture. She will share how the mass implementation of CO2 direct air capture, or DAC, is potentially achieved through distributed capture solutions that can be implemented in mass number and in as many places as possible. DAC is rapidly emerging as a complementary solution to existing climate change mitigation strategies. To achieve distributed carbon capture, recent advancement by our team at SUTD has shown a novel form of carbon capture material that is lightweight and easily integrated into urban spaces. A synergy between film architectural design and device design collectively demonstrate the potential of passive and distributed carbon capture from ambient air. She is currently an associate professor in the Engineering Product Development pillar at SUTD, and she holds 2 appointments as the associate pillar head and the director for the Digital Manufacturing and Design Center, also known as DEMAND. DEMAND's research profile spans the breadth of digital design and manufacturing resources and capabilities that integrate across design, materials, and manufacturing processes. Hong Yi has co-authored more than 150 peer-reviewed publications and is a co-inventor of 30 granted patents. May I introduce our third speaker, Associate Professor, Engineering Product Development Pillar, Lo Hong Yi.
Hello, I'm Hong Yi. I'm an associate professor at the Engineering Product Development Pillar at SUTD. I'm also concurrently the director of the Digital Manufacturing and Design Research Center. I'm gonna go ahead now and share my screen. So firstly, I'd like to thank the organizer. It's a pleasure to be a keynote speaker for the 2022 SUTD's first industry workshop. Today, I'm going to be sharing with you on our recent research related to carbon capture, and it's called direct air capture. I'm sure every one of you listening to this talk have heard of the issues of CO2 level at record high, has heard of the climate change crisis, perhaps so frequent that it risks that some of us become insensitive to the urgency of this crisis. Unfortunately, the CO2 level in our atmosphere continues to rise. There are 2 important information I'm sharing in this slide. Firstly, today in our atmosphere, the CO2 concentration is more than double the CO2 level pre-industrial level. A second important information is that this rise in the CO2 in our atmosphere is associated with the rise of CO2 emission from human activities. And hence the phrase anthropogenic emissions refers to CO2 emissions related to, basically human activities. The primary source of carbon dioxide in our air come from what we call a point source carbon emissions. And these are concentrated CO2 emission primarily from power plants, whether it's coal plants or fossil fuel plants, as well as industries, processes plants. Hence, naturally, the main carbon capture solution today is what is called a point source carbon capture. It essentially refers to capturing CO2 where they are emitted. These current solutions are essentially integrated into existing power plant or chemical plant. Just to give a sense of the scale of today's point source carbon capture technologies, this image shows a representative of what a carbon capture solution look like. And these solutions, as I said, is usually integrated into these power plant or chemical plants, right? And hence the capture at the source of emissions. Point source carbon capture is a fairly mature technology. Today, among all the worldwide point source carbon captured, the technology has achieved a capture efficiency of about 90%. So there is still that residual of 10% of carbon emission that escape into the air. Nevertheless, what this means is that today, worldwide, we are kind of sequestering close to about 40 million tons of CO2. This is far from enough. In order to address the climate change issues, we need to increase the capture capacity to 8 gigaton of CO2 by 2050. So the industries are racing to increase the capture capacity in the point source capture industries. Even if the industries are able to achieve 100% capture efficiency, and that would mean achieving a net zero emissions, we are still far from achieving our goal. Because besides point source emissions, there are also the what is called the distributed distribution. This comes from, for example, the transport industries, the building sectors, as well as agriculture and so on. And not to forget the cumulative CO2 concentration, the historical cumulative CO2 concentration in the air. So to achieve that ambitious goal, we need what's called a negative emission technologies. Negative emission technology generally aims to achieve a net reductions of CO2 in the atmosphere. One such potential negative emission technology is referred to as direct air capture. As the the phrase implied, this means capturing CO2 directly from our atmosphere outside of the point source emissions. Now, there's this challenge with direct air captures. And then primarily today, the cost of direct air capture is at magnitudes of order higher than the point source capture. And that is because of the concentration of CO2 in ambient air being far lower than the concentrated CO2 from point source emissions. Nevertheless, the proponents of direct air captures argue that, with scale, we can reduce the cost of direct air captures. So today we do have a number of commercial direct air capture solutions. One of these pioneer is a company called Climates in Switzerland. And this image shows the direct air capture installations that has been put in place. One of my partners said that if we were to implement today's direct air capture, it would take up an entire Orchard Road, right? So a current technology gap, if you will, in direct air capture is the high footprint requirement that makes this not feasible in urban or in land-surface city area like Singapore. This is where we aspired to offer an alternative to today's direct air capture solution that could potentially be installed in urban cities. Before I go into sharing with you our technology, let me share one of the reasons why today's capture solutions require a fairly high footprint. And that boils down to the type of material that's being used to capture CO2. Generally, these captured material can be broadly categorized into what is called liquid absorbents and solid absorbents. And the picture kind of gives you an image of what this material look like, right? The liquid absorbents, the mainstream material, it's amine chemicals. And these are actually hazardous chemicals that is being used to capture CO2. The solid sorbent, as its name implies, are made out of powder and pellets type of materials. A commonality between these two materials, aside from the differences in their capture performance and capacity and stability and so on, is that these form factors are very inflexible in how one could design the captured device for where they can be used, right? And this is where we come in. we've been working on a carbon capture material in the form of a freestanding film. This image shows you a picture of what looks like a plastic films. In this what looks like a plastic film is our proprietary material formulations, and we are referring to this film as carbon capture composite film, or abbreviating as a C3 film. The film, and it looks like a plastics, passively absorbs CO2 without the need to actively input energy. The absorbed CO2 can then be released on demand for where CO2 are needed. Right. So this is what we call a regenerable carbon capture film. We started this research about 4 years ago, and today in our lab, we are producing meters scale of these C3 films. In addition to the pictures that you see, another aspect of our innovation is that we could control the capture performance through introducing what we call surface texture. By texturing the film, we can control what's called the capture dynamics. The graph over here shows the concentration of CO2 in a controlled environmental chamber. And the different color of the graph shows how fast or how much the film can capture. So while today our kind of a baseline C3 film has a capture performance on par with state-of-the-art carbon capture material out there, our solutions further offer a range of engineering parameters that allow us to tailor and tune the capture performance according to the requirement. Now, in the next few slides, I'm going to show some use case of how C3 film is used in a urban environment. The first example over here is a C3 film installed in a bus stop. Now, many of us who take public transport would know that every time a bus arrives at a bus stop, there is a gust of CO2 that comes from the exhaust. So by performing these tests at the bus stop during a peak hour of between 5 to 6 p.m., we see a surge in the CO2 concentration, what we call the number of CO2 spike at the bus stop, right? By mounting our C3 film at the bus stop, we effectively reduce the CO2 spike at the bus stop, and the film simply sits, passively at the bus stop. So this is one example of how a carbon capture solution can now be implemented in an urban environment. In another example, this was a control test actually done in an indoor environment. So this was done at the Skylab at the Building and Construction Authority in Singapore. So the picture shows two identical rooms with identical setting, identical CO2 emission, right, simulated by a simulated human respiration. And the graph over here shows the measured CO2 level between a room with and without the C3 film. Again, the C3 film are kind of mounted or allowed to place in a room passively. Imagine it like an air filter that we becomes a device that is common in a household, right? An air filter device. So imagine a C3 film like an air filter device sitting in a room, and this graph shows that the presence of the C3 film consistently maintain a lower CO2 level in the room, right? And this translates to almost a liters of a CO2 removal from the room over the test period. Last but not least, through a collaboration with an architecture professor, Professor Thomas Schoeffer in SUTD, and through a Master of Architecture thesis, a standalone tower made out of our C3 material was designed to capture CO2. So this tower, in fact, as we kind of hypothesize the installation of this tower if any one of you recognize, this is a view near the Keppel area in the southern part of the Singapore island. So this could be a freestanding tower made out of C3 material that again captures CO2 without needing additional energy. It just make use of the wind flow in the environment that draw basically air around the towers where the air is essentially cleaned up of the CO2, right? So these three examples that I've shown up until now give us a hope that carbon capture solutions can be done in the city areas. Now, let me extrapolate a little bit more from what we have shown, what we have been studying. This is an ongoing study, but nevertheless, now imagine that a skyscraper can potentially actually, or it's known to potentially emit about 1,000 to 3,000 tons of CO2 per year. Now, if we take the CBD area of Singapore, right, and if we looked at the number of a building that is above 150 meter tall in Singapore, we have about close to 100 of them, right? So just by taking an average numbers, we can postulate the potential of C3 film removing between 150,000 to 3,000 tons of CO2 per year. Now, extrapolating it further, because the C3 film can be installed in essentially any city area. So if we take just the metropolitan area, is the southeast area, totaling the number of tall buildings, we can potentially capture close to 3 million tons of CO2 per year. So with these extrapolations, we kind of, we have these aspirations that building can potentially serve as a carbon capture station. Now, this number may seem to be small compared to the number that I begin with at the beginning of this talk, right? But we believe that every bit of capture count. So our effort now towards, capturing CO2 from city area, we're giving it a name of a carbon beats, and we aspire to bring these solutions to every cities in Asia. At this juncture, I like to thank my team. So this is an effort with what my partner sometimes call partner in crime, Associate Professor Tan Mei Chi, who is also a professor at the Engineering Product Development Pillar, and the research team, Daniel, Kejin, and Ben. So I'm going to stop here. And again, I thank you for your attention and listening to this talk.
Thank you, Associate Professor Loh, for your enlightening speech. And once again, we are deeply appreciative to our distinguished speakers for their time in delivering their perspectives and opportunities on smart application for sustainability. In the next segment of our program, the forum panel will discuss and address the present and imminent global challenges. They will also debate on upcoming research megatrends and the outlook for Singapore's research and development in the next decade.